Alright, what's up, guys? Today we're going to be going over ramp problems for Physics 1, Physics 2, and Physics C. So, a quick concept review. First, you need to know about free body diagrams. So, if you take a look at a free body diagram, you know that a couple of forces can act on it. The two main ones are gravitational force and normal force. But you also have applied forces, which I'll label as FA, and frictional forces, which I'll label as FF. Now, gravity always points downward, so on a ramp, this can have different implications, which I'll go over later. Remember that friction, so the force of friction, is always mu times the normal force. And this can also be written as mu is the force of friction over the normal force. So let's look at a ramp. So we have a box on top of the ramp. We know that there's a force straight down, and that is the force of gravity. And here we have our theta. Now this force of gravity has two components. One is down the ramp, which in this case we'll call down the ramp x. Let me label that in gray. Call down the ramp x, and we'll call up the ramp or perpendicular to the ramp y. So it's a little bit different from our traditional xy plane. We have our x component, f of g of x, which is our force of gravity, which is defined as mg times sine of theta. And I'll show you the trig for that in a second here. And then we have a force down the ramp, or I should say y component of gravity. So FGY equals our mg cosine theta to make up our second component. Now our y component of gravity is the same as our normal force, and that's because equal and opposite forces act to keep the block constantly in place in the y plane. So we'll say FGY equals Fn, which equals mg cosine theta. Now let me show you the trig for this real quick. Okay, so how we got these components, we can see that this FG kind of extends down. More importantly, though, we see that this theta here is created because the green, blue, white triangle that you can see kind of here is similar to this smaller triangle right here. What that means is that this is the opposite side, the FGX. And we know that opposite over hypotenuse equals sine theta. So opposite equals hypotenuse sine theta. And our hypotenuse in this case would be our FG. So our FGX equals our FG sine theta, and the same logic can be applied with FGY and cosines. Okay, so a couple other forces that can be applied is our frictional force. So we have our frictional force here, FF, and this can be frictional static or frictional kinetic. For this, I'll label frictional kinetic. And remember that the force, the net force, would just be our FGX minus our FF. And that's because this normal force and this component of gravity cancel out. Okay, so let's move on to a problem. All right, so we have this problem. A 5 kg block slides down a frictionless ramp inclined at 30 degrees. The ramp is 2 meters long. Find the acceleration and the final speed. So first, what we want to do is kind of just draw our scenario. So let's grab a straight line tool and draw a ramp. And draw our box on top of the ramp. Okay. So the block slides down, and this theta here, theta equals 30 degrees. We know that the mass of the block, I'll write the mass down here, was 5 kg. And the length of the ramp, so the distance along the ramp, equals 2 meters. So label this D, distance. Let's do it down here. Why not? D equals 2 meters. Find the acceleration and the final speed. So first, we need to draw our free body diagram. We know that our force of gravity equals mg. So F gravity equals mg, which equals our mass of 5 times our gravity of 9.8, which gives us, let's see, 5 times 9.8, that's 49 newtons. So we have 49 newtons pointing down. Now, we can apply our formulas. So along the ramp, we have 49, which is mg, sine theta, sine of 30 degrees. And our normal force, which is just our y component of gravity, is our 49 cosine 30 degrees. Now, if we solve both of these, we get 24.5 newtons for this. And 5.9 times cosine 30 gives us 42.4 newtons. Okay. So now that we have that, we want to look at acceleration. Acceleration is just, or mass times acceleration is F. So F divided by m gives us acceleration. The only acceleration we're looking at is down the ramp, so we can disregard this, and we can disregard this. We're just looking at down the ramp. And because there's only one force down the ramp, that's the only force we have to take into account. So we get 24.5 divided by the mass of the block, which is 5, and that gives us a final answer of 4.9 meters per second squared. So that's our acceleration. Now we also have to find the final speed. For this, we can just use kinematics. We know that v final squared equals vi squared plus 2ad. We know that our block starts at rest. Normally it would say in the problem here, but it doesn't say. We could just assume it starts at rest. So we get 0 squared plus 2 times our acceleration is 4.9, as we mentioned in this problem, times d is 2 meters. That's given. So we get Vf equals 19.6, and the square root of that more specifically, which is 4.43 meters per second. Okay, let's move on to our next problem. All right, in this problem, we have a 10 kg block sliding down a 20-degree ramp. So we have our theta equals 20 degrees. Our block is 10 kg, so our Fg equals 10 times 9.8. Coefficient of kinetic friction, 0.2. Find the acceleration. So in this case, what we have to do is we have to find our normal force, and you'll see why in a second. So let's calculate our Fn, which is just 10 times 9.8, which is 98 cosine 20 degrees, which gives us 92 newtons. So we have 92 newtons here. And we have to find our frictional force. So how we find our frictional force is Ff equals mu Fn. This is where our normal force comes in. So we get FF equals 0.2 times our Fn, which is, let's see, 92. And when we solve that, that gives us 18.4 newtons. Now that we have a frictional force, we can calculate our gravitational force to calculate the net force. Our gravitational force is our 98 sine 20 degrees, which gives us 15.6 newtons. And we found our frictional force to be 18.4 newtons. Now, our net force, F net, equals our sum of forces, which is, if we're calling this positive x, is 15.6 minus 18.4. Now, that equals negative 2.8 newtons, which in this case means that the block slides slowly or it stopped. Because this is a frictional force, more likely it's just stopped. Because this is a frictional force, it can be less than or equal to 18.4 newtons. And it would be less than 18.4 newtons in the case that the FGX is less than 18.4 newtons. In this case, frictional force is most likely actually applying only 15.6 newtons of force. And that would just stop the block. So, in that case, our acceleration would be 0 meters per second squared. And that's because our frictional force would really only be 15.6 newtons. So this would be 0 newtons. Okay, let's move on to the next problem. All right, so if you're using this video to review for an AP exam, this problem is especially useful. If not, and if you haven't gotten over springs, you might not understand this problem just yet. So go ahead and use that information how you will. So our spring here would kind of just be like that, and the block is essentially colliding with the spring. And what we're trying to find is, what is this value here? How much does the spring compress? So we have a lot of information here. That's why I wrote it all down. And what we can do here is that we can actually use energy. So we know that PE equals mgh. If you haven't watched my video on potential energy and kinetic energy, I highly recommend it. It is in the card above, so go ahead and check that out if you haven't. But PE equals mgh, which equals mg times... Now, our height here is a little bit different than just our distance. It's actually this distance right here, that value right there. I'll label it something different than d. What that value turns out to be is d sine theta, and I'll explain that to you in a second. Okay, so let's say we have our ramp here. D is this kind of side here, and h is right here, and we have a theta here. So if we look at this, we can see that opposite over hypotenuse equals sine theta. Our opposite side is h, our hypotenuse is d, equals sine theta. And when we reorganize this, we get h equals d sine theta. So that's why we're using d sine theta instead of h here. Let's get rid of that though. Okay. So we have this equation. We also know that our work done by friction is our friction force times the distance over which the block travels, which is d. And we know that our frictional force is just our mu times our normal force, which is mu mg cosine theta, and our d stays the same, so we got our d here. And finally, we know that our potential energy by the spring, So I'll label this potential energy sub gravity, potential energy sub spring, is 1/2 kx squared. And that should be given to you on the equation sheet. Now, how do we balance this equation? These equations, I should say. Well, we know that our initial energy, so energy initial, equals our energy final. What we also know is that at the bottom of the ramp, we have the potential energy plus our change in kinetic energy, which is equal to work. So right here, right before it touches the spring, we have just these two energy values. And right after it touches the spring, we have this energy value. Because initial energy equals final energy, we know that PEF minus change in KE. This is minus because at the bottom, you don't have as much potential energy, meaning you're taking away whatever the kinetic energy was, whatever kinetic energy was applied. And I'll explain that a little bit more clearly in a second. Equals our final energy, which is 1/2 kx squared. So, as promised, let me explain this a bit more clearly. At the top of the ramp, we have our maximum potential energy gravitational. At the bottom of the ramp, we don't have as much potential energy gravitational. And that's because the work done by friction takes away from the energy. The work done by friction in this case is negative because friction points in the opposite direction from the distance, or from the direction that our block is moving. So this is direction of movement, and this is a frictional force. Because frictional force is away from the direction of movement, our kinetic energy has to be a negative value. And that is a little bit tricky. If you don't understand, drop a comment below and I'll get back to you. But I tried explaining it as clearly as possible. Okay, so now we plug everything in and we solve. Our potential energy gravitational, which I'll put in yellow, would be 5 times 9.8 times distance, which is 3 sine 30 degrees. And then I'll put our work in red, minus mu 0.1, 5 times 9.8, cosine 30 degrees, times 3. And then finally we have that all that equals our spring, which is 1/2 times 200 x squared. So now we do all that, we solve for x, and we get that the spring compresses 0.78 meters. So essentially, when the block slides down the ramp and hits the spring, this spring will compress to this value, which is 0.78 meters. All right, hope that makes sense. Let's go over to some key takeaways. All right, so number one key takeaway is always draw a diagram. Diagrams are so useful in these types of problems, so make sure you always do that. You also want to identify forces. So forces, make sure you have your Fn and your Fg always. Sometimes you may have an Ff, force of friction, and you may have an Fa, which is force applied. These might or might not be in ramp problems. These two always are in ramp problems. So you can also, as we discussed, use energy to help with some of these ramp problems. And friction may stop motion from happening, as we discussed in another one of the problems. And on the AP exam, you often have combinations of concepts. Of concepts. So keep an eye out for that. All right. If you guys have any questions, please leave them in the comment section down below. I hope that you enjoyed, and I hope that I provided you with a better understanding of ramp problems. I know that there were a couple parts that were a little bit confusing, so if those don't make sense, hit me up. But other than that, I hope you guys have a great rest of your night.